time silently shapes the evolution of our existence, constructing the framework of our lives using the building blocks of hours, seconds, and minutes. As time progressed in the universe, everything unfolded from the Big Bang to the birth of our own sun. The steady tick of the clock may appear uniform, yet, according to the insights of scientists like Albert Einstein, time is not a constant. It is relative. Its flow is influenced by gravitational force. Even on our home planet Earth, time can elapse at different rates depending on geographical location. The gravitational force acting on an object is less at the equator when we compare it to the poles. Consequently, the passage of time for an individual situated on the equator would differ from that of a person at the poles. And due to the same gravitational force difference, GPS satellites become faulty. Considered as the weakest fundamental force, gravity, when it takes charge, it gives rise to the most potent destroyer of the universe, the black holes. In the space where black holes rule, time slows down. Black holes are really mysterious and strong. They can bend time and space. Inside them, time stretches in a way that's hard to understand, and the law we follow breaks down at these extremes. Today, I invite you to accompany me on an exploration, delving into the profound influence that black holes exert on the very essence of time itself. The Big Bang, happening 13.8 billion years ago, was when the universe began from a small, dense fireball that exploded. Before that, there was no concept of time. After the Big Bang, time started ticking and space began to expand. Over time, primordial stars emerged, eventually leading to the formation of the first black holes upon their demise. These black holes now reside at the centers of nearly all galaxies, each holding masses exceeding 1,000,000 times that of the Sun. But with all this, an intriguing question arises. What is the connection between time and black holes? Why does time seem to slow down near these cosmic heavyweights? The key lies in the force of gravity. Black holes possess the most potent gravitational force among all celestial objects. Anything approaching them is held captive by their gravity, to the extent that not even light can flee. The origin of this formidable gravitational force is rooted in the mass of black holes, which warps and contorts space-time in ways beyond imagination. However, if we deem black holes as peculiar, the very fabric of space itself proves to be even more enigmatic. Although space is often considered a vacuum, it is not a flawless one. Intergalactic space contains a sparse scattering of hydrogen atoms per cubic meter, dispelling the notion of a perfect vacuum. But then another basic question prompts, and that is, what is the time? In reality, everything, from atoms to black holes, occupies space, and the rate at which entities move through space serves as a measure of time. The relation between space-time and gravitational force was established by Albert Einstein in his theory of general relativity in 1915. He proposed that gravity is not a force between masses, as described by Isaac Newton, but rather a result of the curvature of space-time caused by the presence of mass and energy. According to general relativity, massive objects like planets and stars cause a curvature in the fabric of space-time around them, and other objects moving through this curved space-time experience what we perceive as gravitational attraction. Later on, the famous mathematician Hermann Minkowski combined space and time into one thing and named it the space-time. According to him, everything happening in the universe involves both space and time at the same time. He saw space and time as two connected aspects, woven together into a continuous fabric known as space-time. This fabric can bend or warp when there is mass and energy around it. Anything like a star, Earth, or even an ant bends space-time, but it depends on how massive the body is. This space-time creates a four-dimensional universe in which fourth dimension is the time. In the domain of special relativity, every object moves at a consistent speed through both space and time. Put simply, whether an object is at rest or moving at the speed of light, Its overall speed in space-time remains steady. When an object travels at speeds slower than light, it covers less distance in space, prompting time to pass more quickly to make up for the difference. Conversely, if the same object accelerates to the speed of light, it covers more spatial ground, causing time to slow down. This fascinating phenomenon, where time behaves differently based on the object's motion, is known as time dilation. It's a unique aspect of Einstein's theory that shows how our perception of time can vary depending on how fast things are moving. Now let us understand how black holes are able to slow down the time. To unravel this, let's first look at the crucial components of black holes. There are four main parts. The first is the accretion disk, where matter moves at the speed of light. This is the only visible part to us. The second is the photon sphere, where incoming light or object revolves around the black hole without moving closer or farther due to gravity equilibrium. The third is the event horizon, a region so gravitationally strong that nothing, not even light, can escape. It appears completely black. The fourth is the singularity, an infinitely compressed point mass responsible for the drastic gravitational force. Now let's come to the point. As an object approaches a black hole, it moves closer to the event horizon, where its velocity tends to approach the speed of light. During this process, the gravitational field near the black hole causes the object to appear to cover more distance in space. To compensate for this, time dilation occurs, and time starts to move slowly. This happens due to the fact that the intense gravitational force of the black hole distorts the space-time curvature, creating a steep well. Within this well, the object can reach speeds approaching the maximum speed of light. At the bottom of this well lies a singularity, where the predictions of our current physics break down and time essentially comes to a halt. So basically, time slows down because the light or object could not come out of this ruptured well. When someone outside a black hole watches an object getting closer to its center, the strong gravitational effects make the object appear almost stationary. What actually happens is that it took a normal amount of time from the viewpoint of the inside black hole object because it was traveling into the infinite distance of space created by the steep well of the black hole. However, the distance it covers becomes practically invisible to the external viewpoint. This creates the illusion that the object has stopped, making it seem like a very long time has lapsed. This phenomenon, known as gravity time dilation, occurs because the intense gravitational field slows down time for the object. In reality, both the object and the observer experience the same amount of time, but the outside observer's perception is distorted by the invisible space near the black hole. In actuality, time doesn't slow down near a black hole. Rather, it's just that the distance an object needs to cover becomes infinite. This phenomenon is solely attributed to the gravitational force, showcasing the impactful influence of the universe's weakest fundamental force. But here a question arises: is this solely a theoretical concept, or do we possess evidence to substantiate it? Before exploring this inquiry, here's a question for all space enthusiasts. Considering the scenario where someone might enter a black hole, which presents a higher risk, a smaller-sized black hole, or a larger one, share your thoughts in the comments section. Now, as for the evidence of gravity time dilation, scientists have observed this phenomenon in the real world on a regular basis. When light rays pass through massive objects like galaxies or stars, they lose energy due to the curvature of space-time. In simpler terms, as light traverses the gravitational well, it covers a longer distance and experiences fatigue, resulting in a redshift. The bending of space-time increases the distance between us and the light, requiring the light to travel further and, consequently, slowing down time, a phenomenon known as gravitational redshift. Now, this is all about the time dilation, and I really hope that this video explains how the time slows down near a black hole. And while we are talking about the black holes, have you heard about the second largest black hole? The colossal black hole, which harbors an astounding 66 billion solar masses. If you're intrigued by this enigmatic entity, The following video provides more insight into its fascinating characteristics.